And MD Majibul Haque will be talking about controlling spin rectification photovoltage in ferromagnetic wires. If you could share your screen, please, MD.
Can you hear me? Hello?
Yeah, we can hear you there. Thank you.
Okay. Okay, so welcome to my presentation. This is Majibul Haque Babu. The title of my presentation is
Oh, sorry,
Controlling
I think we're seeing
Spin-Rectification.
your like presentation screen instead of the slides.
So you cannot see my presentation?
No, we're seeing like the slide and the next slide. We're not seeing the actual screen.
Oh, okay. So you can see my two screen?
Yes.
Yeah.
So okay, I think okay, so the screen two, you can see this one. So okay, so now you can see only one screen?
Now it's like the presentation screen where we see your next slide.
If you go to display settings on the top, I think you can adjust this.
Yeah.
So if you share again and then go to display settings.
Should do this. I think I can. So now you can see this one only, right? Can you see only one slide?
Yeah, perfect. Thanks so much.
Okay. Okay. So, okay, so this is my title. I already mentioned that this one is. So now can you see only one slide?
Yes, looks great. Thank you.
Okay, so this is the control. So this is my title, controlling spin rectification photovoltage in ferromagnetic wires. So this is my title of my presentation. So at first, I'm going to discuss about the introduction physics of spin rectification under FMR, and this is the experimental setup. Then I will discuss about the experimental setup. Then I will discuss about the result, and finally, I will discuss about the summary of my research. So now, so this basically represent the fundamental mechanism of the spin rectification under ferromagnetic resonance. So at first, when we apply the microwave current to the ferromagnetic sample, then it's basically generate the RF magnetic field, which basically drives the magnetization into precision. So at this point, two important things happen simultaneously. So at first, the system reaches the FMR condition when the frequency of RF magnetic field matches well with the non-natural precision frequency of the magnetization. So at this resonance condition, the precision amplitude of magnetization becomes maximum, right? So now, so then the leading to maximum absorption of the micro power here you can see, and the second one at FMR magnetization, as magnetization precesses continuously, so its angle changes with respect to the current direction. So now this variation then generates an oscillating resistance because of the anisotropic magnetic resistance effect. So then both RF current and the resistance they oscillate with the time. So then they're mixing product produce a nonlinear term using this expression. So then the time average component of this term, which can give us the rectifications, I mean the voltage signals, which we call the spin rectification photovoltage. So now we can see the spin rectification occurs precisely at FMR, where both the maximum power absorption and the spin rectification photovoltage take place simultaneously. So now this is our experimental setup. So this is our experimental setup. So now you can see using a bias T, we are able to supply both DC and the RF current to the sample. So now here you can see the sample is the nickel iron wire with the diameter 50 micrometer, which basically terminates a coaxial cable, which is basically used to deliver both DC and the RF current to the sample. So as I said, in the spin rectification mechanism, we typically use the RF current to excite the magnetization through the RF field, which basically drives the FMR. So now, but in that case, the signal's amplitude is pretty small in experimentally. So to improve the detection level, so then we apply the small amount DC current because it is well-known information that the amplitude of the voltage is become larger in the presence of the DC current. So now, by the way, this is the microscope view of the wire connection. So now you can see on the left-hand side, we use basically the soldered indium contact, and on the right-hand side, we use a conductive silver paste contact. So now you can see here the dashed region basically marks the silver covered area, and the uncovered part defines the effective length of the wire, which basically contributes to the spin rectification photovoltage. And so now I just want to tell you one thing, since only the uncovered segment carries basically the, the both DC and RF current, which also experiencing the magnetization precision. So this portion is basically the active region of the of our device actually. So then after each measurement, we basically extending this silver paste slightly, so then which gradually shorten the effective length of the wires, and that way we basically study how the spin rectification photovoltage changes with the effective length of the wire. So now this slide basically shows the FMR results in a parallel magnetic field. So now in figure 8, you can see which basically represent the microwave absorption peak at 0.5 kilovolts, which basically confirms the ferromagnetic resonance at 7 gigahertz. And this figure basically represents the photovoltaic peak that basically appears at the same resonant field, so which basically proving that the signal comes from the spin rectification during FMR at 10 milliampere DC current. And by the way, so you can see there is an insect image which basically shows the ratio of the photovoltage to the DC current, which basically represents the FMR induced resistance oscillation, which we call the extra resistance, so which is basically with an amplitude delta R is 10 milliohm at 10 milliampere DC current. So that means we can say this spin rectification photovoltage basically originates from a resistance change during FMR. So now let's see how this voltage and this resistance, the extra resistance, changes with the applied DC bias current. So now for the 1.3 millimeter long wire, we check basically how this voltage and the resistance behaves as a function of the DC bias current. So now, as you can see, the spin rectification photovoltage increases linearly with the DC bias current. By the way, here each data point was obtained from a single FMR measurement, which is taken at a specific DC bias current. So now you can see the resistance, the extra resistance stays constant at around 31 milliohm, which means that the extra resistance at FMR does not depend on the DC bias current. It basically appears only in the presence of RF current, which confirming that this effect is FMR driven spin rectification. And by the way, we know that the DC bias does not modify the magnetic precision itself, but it likely influence the phase relationship. So therefore, we can say the amplitude of the photovoltage changes with the DC current. So that means in our case, this enhancement is attributed to a change in the phase shift conditions. So that means our photovoltaic signal, the spin rectification photovoltaic signal is really phase sensitive. So now this slide shows the how the spin rectification photovoltaic signals changes with the wire length, the effective wire length. So now you can see the solid square show the slope values, which is basically extracted from the IB measurement, and the open circle basically show the amplitude of the photovoltage at 10 milliampere DC bias current for each measurement. So now here you can see the both increases linearly with the effective length of the wire, which means that the FMR induced extra resistance also increases with the effective wire length. So now this behavior is the same as the normal wire resistance. So therefore, we can say that our results confirm that the spin rectification photovoltage and FMR induced resistance changes linearly with the wire length. So this is the summary of my research. So in this work, we investigated the spin rectification in nickel iron wire under ferromagnetic resonance. By analyzing wires of different length, we observed that the spin rectification voltage increases linearly with the wire length. And furthermore, FMR-driven resistance exhibits the same length dependence as the normal DC resistance. So now we can say that these findings basically demonstrate that the spin rectification, this photovoltaic signal can be conventionally controlled through the simple geometric modification in metallic wire-based spintronic device.
Oh, thank you very much for a really nice talk. So we have time for a quick question if we have any. I think I'd wondered if you'd seen any effects of frequency in the FMR measurements, or if you just saw, I think you mentioned you had one peak at 7 gigahertz. Did you see any variation of this with the
Can you say one more time?
Sizes?
Can you say one more time?
Did you see any variation in the frequency that you need to use for the FMR measurements? Yes.
So we did the frequency dispersion study in our previous paper. Then we confirmed that yes, our experiment, our material does show the FMR, the frequency dispersion. And then we see the gyro-magnetic ratio is good.
Okay, so that was the previous work. That sounds good, thank you.